All right, since we ran out of time, I wanted to stay on task, and so I'm making this video about center of mass. So hopefully you understand it and how it's related to this chapter. So basically, when we have the center of mass, there's a couple different reasons that we might find this interesting or of use to us. And the center of mass can refer to either a collection of objects. So if we have several different little masses all spread over a space, a volume in space, we can find the center of mass of that collection. And what it is it's really the location where you could say, because of considering how much mass is it at each location individually and where it's located, the center of mass is really, it's a weighted average of the position, that you could replace all your collection of objects with a single mass that's equal to the sum of all the individual masses. And if you put it at that location, it has exactly the same effect. Another way of thinking about it would be like if we wanted to balance our object at that location, if we wanted to balance all those masses, if we wanted to put a little, pivot point there, that's the location where we would put it. It can also refer to an object that has its mass distributed over a large volume. So if I have a very large sphere, like the Earth, its center of mass is where I could consider its mass to be concentrated. Even like a donut, the center of mass of the donut would be where all its mass could be considered to be located. So that's what we mean by the center of mass. So I said it's a weighted average, and if you think about how you calculate the average, like if you take an average number, you add up all the numbers and then you divide by however many numbers you had. The center of mass is kind of like that, but it's a weighted average. So when you're looking at the position expression, each position vector for each individual object is then weighted by the mass. And so we see, instead of just taking all the positions and adding them together, we take the product of each individual mass and its position, and then we add those together, and then we divide by the total mass. This is a little bit more of a concise way to write it, where we're using the summation signs. Remember, that means adding. And so adding over all the individual objects means that this would be the same thing as what we see over here. So if I wanted to use that expression, so we have the center of mass expression in vector form, look like the m sub I r sub I over the sum of the m sub I. We can sort of break that down into the different components using the different, it would be the sum of the m sub I times the x coordinate of where they are, and then the y center of mass location, you would take the mass times the y coordinate and then divide by the total mass, and then finally the z component would be the summation of the mass times the z coordinate over the total mass. And so it's as simple as that. So let's look at how we might use this. So here's an example. I have three masses, and they're at these different coordinates. This is the x coordinate and this is the y coordinate. And we want to find where's the center of mass of these three blocks. So if I want to find the x center of mass, I'm going to take the first object, its mass is 0.3 kilograms, and then its x coordinate is 0.2. Then I look at the second object, which is 0.4 kilograms, and its position is at 0.1. And then the last one is 0.2 kilograms, and its position is at minus 0.3. So those are our x positions times the mass, and then I add up all the masses, 0.3 plus 0.4 plus 0.2. And so on the top I have 0.06 plus 0.04 minus 0.06 divided by 0.9. I notice these two would cancel out, so I'm just left with 0.04 over 0.9, and I get a value of 0.044 meters. So that is the X center of mass position. I would do the Y center of mass similarly. Taking the mass times the Y coordinate this time. I already know what the masses add up to be, so I'm not going to write them all out again. And this time I got the Y coordinate. And you know what? I think I made a math mistake when I first added them together, so I'm going to check this really quick. Yep, I did make a math mistake the first time, so it actually is kind of interesting. We have these X and Y coordinates of what this means is if I took one mass, I could take these three masses of chocolate blocks, substitute them with one mass of 0.9 kilograms, and I would place it at this X and Y coordinate, and it would be exactly the same situation if I did that. And that's where how we mean the center of mass. Or if somehow I was able to balance these objects, they would balance at this center of mass position. All right, so objects that are nice and symmetric are really nice because the center of mass is easy to find because it's actually at the geometric center of the object. So here are some examples for the cylinder, the sphere, and the cube. It's, right at the very geometric center. And in other cases, if we, sometimes we can do this through integration, but we won't be doing that this semester. Sometimes we can say that if there's an axis about which the object is symmetric, then the center of mass is also going to be on that axis of symmetry. The donut's an interesting case because here is where the center of mass is. Notice this would be the axis of symmetry for the donut, and even though the donut actually doesn't exist in its whole, that's still where the center of mass is. So it's a good question. Sometimes you're asked, does the center of mass of an object have to lie on the object? And the answer is no, it doesn't. A donut's the perfect example of a case where it does not have to lie there. Okay, so here's a question I want you to think about. There must be equal amounts of mass on both sides of the center of mass of an object. So in a sense, we could even go back to our example for the chocolate blocks, because we could think of that as an example. I know it's not a single object, but it ends up having sort of the same effect. So our chocolate block had a mass at 0.2 and 0.3, so here was one block. This was 0.3 kilograms was here, and the other one was 0.1, and then down, that's where there was a 0.4 kilogram block, and then there was one at 0.3, and then up 0.6, which is actually like way up here, and this was 0.2 kilograms. We ended up finding that our center of mass location was really kind of like somewhere around here. And if you look at this doesn't have equal amounts of mass on both sides of the center of mass. That doesn't work out that way. Another example that I like to give is the seesaw. Because if you've played on a seesaw, the balance point, the point where the seesaw will balance, is also the center of mass. And if you remember, like if you've ever played on the seesaw when you're little, if you wanted to balance with your friend, it always depended on, who was the larger kid. If you're one of those little petite kids, you had to really kind of go far out on the seesaw to balance one of your bigger friends. Maybe it's someone's older than you. The larger person has to go closer, and the smaller person has to go further away. And in both these cases, we don't have the same amount of mass on both sides. And so this is not true, because center of mass is a weighted average, and so the mass weights the position. It's not just putting the same amount of mass on both sides. So a similar question here, if you put two objects together and then we found the center of mass. So we have the yellow block and the red rod are joined together, and they're asking you, the X is where the center of mass is. And they're basically saying, does the yellow block or the red rod have more mass? Now, one of the ways that we can think about it is, where is the center of mass of each individual object? Because, how do I find, like if I wanted to, for the yellow block, how would I write its position? Well, you would write its position by saying where its center of mass is. So it only has the center of mass of the yellow block is right here, and then the center of mass of the red block is right here. And so you could see that because the red block is more extended, now it's supposed to be in the middle, so just pretend it's in the middle. Since this distance is bigger, and it balances out with this smaller, basically the X of the yellow block times the mass of the yellow block has to be equal to the X of the red block times the mass of the red block, in order, then that tells you the center mass is right in the center. And so because the X of the yellow block is smaller than the X of the red block, that means the mass of the yellow block has to be bigger than the mass of the red block. And so the yellow one has the greater mass. Now, sort of one of the reasons that we look at center of mass for this particular chapter is, we can actually use this idea to help us think about how an object that isn't like a point mass, how does it move? So a lot of times when we're talking about objects, like throwing a ball through the air, the ball's easy to follow, it's very symmetric, we can just follow its center. But in this picture you can see, what if I threw a wrench instead of a ball? How do I figure out the motion of the wrench? Because the wrench is going to like rotate as it goes through the air, and how am I supposed to like compensate for that? Well, what we can do is, look here, they're following the white dots are the center of mass of the wrench, and notice how that takes a pretty constant path through space. So following the center of mass of objects helps us understand their motion. We don't have to do all the complicated rotation here, but we can just follow the center of mass. So just as we start off with the X center of mass, or maybe I should write it as the position is equal to the sum of the m sub I times the r sub I divided by m sub I. And we can, this is just the total mass. We can take m times r, I'm just rearranging this. If we take the derivative of this with respect to time, we get this expression. And so we can sort of work from the center of mass position, and then we get into this, what about the velocity of the center of mass? Well, we can find that just as easily by looking at the individual momenta of each of the particles. Adding them all together gives me the total momentum of the system. So I can find the total momentum of the system by adding up the individual momentum of each particle, or I can just take the total mass of all the particles and multiply that by the velocity of the center of mass. And this is how we can take a whole collection of objects and work with them a little bit more easily, because I can just treat them like one object moving with a particular velocity, and that's the velocity of the center of mass. So we can take that one step further and we can say, okay, well, what about the mass times acceleration of the center of mass? Well, that's just the summation of each mass times its individual acceleration. Now, we know F equals ma, so for each m sub I, a sub I, it has two kinds of forces that might act on it. So we're looking at all the forces acting on one individual object. It can be the external forces like gravity, but then also the forces that we would call internal forces. And this would be like, so if I have, say I have object 1 and object 2. When I'm looking at the forces on object 1, I might have gravity might be acting on it, there might be friction acting on it, but then there also might be a force on object 1 that comes from object 2. These are like the action-reaction pairs. And if I look at then all these, when I add these forces together, the action-reaction pairs cancel out, because I'll look at forces acting on object 1 from object 2, but then I'll have a force from object 1 acting on object 2. Those are equal and opposite, and they cancel out. And so when I do the summation, MACM is equal to these, all I'll get left is all the external forces. And so this becomes a way that I can treat a system of particles, is I can just look at all the external forces, and this what causes the center of mass of the whole system to move. So here we see a picture of this. Here we have a shell that's shot into the air. Notice it's going to take what we would imagine would be a projectile path. This is the path of the center of mass, is the pink. But at some point it explodes. Now we have two objects that are moving, and you can see they're moving differently, but the center of mass is still following the projectile path. And that's sort of the idea, that instead of following each individual piece of the shell and trying to figure out which individual piece goes, we can still say that the center of mass is going to follow a path given by whatever the external forces are acting on it, which in this case would be gravity. And so that's sort of our summation of how we calculate center of mass, and also how we would use it. And that will finish us up for chapter 8. Next time we'll be able to start chapter 9.